For 1 million years, somewhere in the long past of this planet, the sky refused to stop raining. Not for a season, not for a generation, not for 10,000 years. For 1 full 1,000,000 years, water fell from a Pangaean sky that had spent the previous 15 million years almost entirely silent. By the time the rain finally let up, the Ruasukians who had ruled the land were vanishing. The first stony coral reefs were dying, the conodonts were collapsing, and a small lineage of light-footed bipeds was walking out across an empty continent for the first time. Tonight, we follow that storm from the moment it began to the world it left behind. Settle in and do me a small favor. Tell me in the comments where in the world you are listening from. Part 1. The day the sky refused to stop raining. Imagine, for a moment, that the rain begins one afternoon and does not stop. Not for a season, not for a century, not for 10,000 years. Imagine that the rain does not stop for 1 million years. This is not a thought experiment. This actually happened on this planet 234 million years ago, in a stretch of the late Triassic that geologists now call the Carnian Pluvial episode. The world we are about to enter was a world tuned for desert. Pangaea, the supercontinent, sat under a sky that almost never opened. Most of its interior was a continent of dust and salt flats. The animals that ran the place were built for heat, for thirst, for endurance. Then, somewhere in the eastern Pacific Ocean of that long-vanished world, the seafloor cracked open. Magma began to surface. Mercury began to rise on the wind. Carbon dioxide began to climb. And the sky, slowly at first, then all at once, refused to stop raining. You will hear me use a few different names tonight, so let me settle them now. The same event is sometimes called the Carnian Humid episode, sometimes the Carnian Pluvial event, sometimes simply the CPE. The names matter less than the thing itself. What matters is that for somewhere between 1 and 2 million years, the entire global climate switched into a state we have almost no good modern analogue for, and almost everything alive at the time had to either move, adapt, or die, and many of them died. The phrase million-year storm sounds like hyperbole. It is not. It is the geological reading of the rocks. Every sedimentary basin we have studied that contains Carnian-aged rock shows the same signature, give or take a few 100,000 years. Across what is now Italy, what is now Austria, what is now China, what is now eastern North America, what is now the southern Andes, the colour of the rocks changes, the texture changes, the chemistry changes, the fossils change. The world, all at once, becomes a different world. And then, just as decisively, it begins to dry out again. The strange part is, you have probably never heard of this. You have heard of the end Permian extinction 252 million years ago, the worst mass dying in Earth's history, the one that almost ended life altogether. You have heard of the end Cretaceous extinction 66 million years ago, the one with the asteroid and the dinosaurs. There is a hidden cousin between them, and it is the one we are spending the next 2 hours with. It was named in 1989 in a paper by Mike Sims and Alistair Ruffle, 2 British geologists who had been looking carefully at how rocks changed across Europe in a particular slice of the Triassic. They noticed that the same change appeared in basin after basin, country after country, at the same point in the rock record. Red beds gave way to grey shales. Salt flats gave way to coal-forming swamps. Reefs collapsed. Whole groups of animals disappeared from the layers above, where they had been thriving in the layers below. They published the observation. The science was quiet for a while. And then, gradually, over the next 30 years, paleontologists realized what they had really found. What they had found was the hinge. The CPE is the moment when the old Triassic world, dominated by crocodile-line archosaurs and seed fern forests, breaks. And in the rubble, the new world starts to assemble itself. Modern conifers diversify. The first stony coral reefs that resemble modern reefs begin to recover. Calcareous nanoplankton appear in the oceans for the first time, quietly inventing the modern carbon cycle. The first lissamphibians, the first turtles, the first true plesiosaurs, the first lepidosaurs, the first pterosaurs, known from substantial bone material, they all appear, or take off, in the post-CPE window. And among them, walking out into a planet that had just been emptied of its old rulers, were the dinosaurs. They had existed before the storm. We have a few footprints, a few small bones from southern Pangaea that suggest small bipedal proto-dinosaurs were running around in the dry years before the rain. But they were marginal animals. They were not the apex of anything. They were less than 5% of the vertebrates we find in pre-CPE rocks. After the storm, that figure starts to climb. Within 30 million years, dinosaurs are 80% of the terrestrial vertebrate fossils we recover. The rain, in other words, did not just kill the old world. It opened the door to the next one, and the dinosaurs walked through. Some paleontologists now argue, in print, that the Carnian Pluvial episode deserves a place in the textbook list of major mass extinctions. The Big Five, as it has been taught for the last 40 years, was canonized by David Raup and Jack Sepkoski in 1982, before any of this work on the CPE existed. The science has moved on. The textbook list has not yet caught up. Whether or not the CPE crosses some particular statistical threshold is, I would suggest, beside the point. What matters is that this is the event that built the world we live in. Tonight, we will follow that storm from beginning to end. We will stand on the deserts of pre-CPE Pangaea and feel the wind. We will watch a piece of ocean floor crack open and begin to bleed basalt. We will see the rain arrive, and we will see what it killed. We will follow the footprints of the first dinosaurs as they fan out across a wet new continent. We will see the rivals they replaced. We will trace the rain forward into the modern atmosphere, the modern oceans, the modern reefs. And, at the end, we will ask the question that this story always ends on. If the world has reset itself once before, on the strength of one volcanic province in the eastern Pacific and 1 million years of rain, then what, exactly, is happening to it now? There is something quietly moving about the way the science of this event has come together. It did not come from a single dramatic discovery. It did not come from a fossil bed full of dinosaur bones or a smoking gun layer of asteroid debris. It came from patient stratigraphy. It came from people who looked at thousands of meters of rock in mountain after mountain and noticed that the rocks were telling the same story in the same order on every continent. It came from chemistry experiments on tiny samples of carbonate, on the lookout for parts per thousand shifts in carbon isotope ratios. It came from track surveys, conducted by pairs of paleontologists walking ridge by ridge with measuring tapes and field notebooks. It is a triumph of slow, careful, ordinary science. And what it has uncovered is one of the most extraordinary chapters in the history of life. Stay with me. The story we are about to tell is the most consequential weather report in the history of the planet, and almost nobody has ever heard it. Part 2. A world that should not have rained. Before the rain came, there was a continent that should not have rained. Pangaea, in the early Carnian, was the largest single piece of land that has ever existed in the history of the planet. From its eastern shore to its western shore, you could, in principle, have walked 9,000 kilometers without seeing the sea. And the sea, in any case, would not have helped much. Most of Pangaea's interior was so far from any ocean that no ordinary atmosphere could move water across that gap. The result was a continent of extreme dryness. Geologists, when they look at rocks from the early Carnian, find the same signatures over and over again. Red beds, where iron oxidizes in the open air. Evaporites, where ancient seawater has been concentrated and dried, leaving sheets of salt and gypsum. Dolomites, the calcium-magnesium carbonate rocks that form in highly evaporative environments. Aeolian sandstones, with the cross-bedding patterns of huge migrating dunes. These rocks tell us, without ambiguity, that the world we are talking about was a desert world. The numbers, where we can estimate them, agree. Atmospheric carbon dioxide sat at around 700 parts per million, more than 1.5 times the modern value, although that comparison can mislead because the rest of the system was so different. Oxygen levels were probably between 15 and 18%, a little below modern levels. Methane was higher. Average global temperature was hot. The interior of Pangaea, in the height of summer, may have reached daytime surface temperatures above 50 degrees Celsius. The air was dry enough to crack the nostrils of anything trying to breathe in it. Pangaea was not, however, completely lifeless. There was an atmospheric system at work that geologists call the Pangaean megamonsoon. Picture this. The supercontinent straddles the equator. In summer, the northern hemisphere heats up. Low pressure forms over the northern interior, and moisture is sucked in from the eastern Tethys Ocean, the long blue arm of water that wraps around the eastern flank of the continent. In winter, the system reverses, and dry continental air pours back out toward the sea. The result is a continental-scale monsoon. Some bands of Pangaea got rain seasonally, briefly, intensely. Most of the continent, most of the time, did not. Within those wetter bands, life thrived. There were forests, of a sort. The dominant plant group across most of southern Pangaea was the Dicroidium flora, a group of seed ferns with a distinctive forked frond morphology. They were not trees in the modern sense, but some of them got large, and they formed gallery woodlands along seasonal rivers and around seasonal lakes. Further north, you would have found a mix of early conifers, bennettitales, those cycad-like plants with elaborate insect-pollinated cones, now extinct, and various lycophytes and sphenophytes around standing water. The animal world was an animal world that we, modern people, would find almost unrecognizable. Walking the Carnian terrain, you would not have seen a single mammal larger than a small rat. You would not have seen a bird, because birds did not yet exist. You would not have seen anything that looked like a modern lizard or a modern snake. The Lepidosaur lineage was just getting started. What you would have seen, mainly, were the pseudo-Suchian archosaurs. This is the lineage on the crocodile side of the great archosaur split. They had, by the early Carnian, occupied almost every available terrestrial niche. The largest predators were rauisuchids, 6-meter, broad-skulled, often quadrupedal predators. The most spectacular of them was Saurosuchus galilei, an apex carnivore from what is now Argentina, with a head the size of an adult human's torso and a bite that probably handled almost any contemporary prey. Picture something built like a barrel-chested bear walking on 4 legs with a lizard's tail and a skull engineered to crush. Atosaurs were the armoured herbivores. Their backs were paved with bony plates, fused together into something close to armour. They moved heavily and slowly through the seasonal forests, browsing low vegetation, looking, if you squint, like crocodiles dressed for a medieval war. Phytosaurs, also pseudo-Suchian, dominated the rivers. They had long, narrow snouts and sharp, conical teeth, and they hunted fish and amphibians at the water's edge. They are not crocodiles, although they look more like crocodiles than crocodiles do at this stage in history, a beautiful example of evolutionary convergence. Among the synapsids, the lineage that would eventually produce mammals, the dominant group was the dicynodonts. Imagine a barrel-bodied, beaked, tusked herbivore the size of a cow or a small ox. Some of the largest, like Stalacaria, could reach 2 meters in body length. They worked the open plains and the wooded margins, browsing on dicroidium and other tough vegetation. They had been, in the Permian, the absolute dominant land vertebrates of the planet. By the Carnian, they were already in slow decline, but they were still abundant, still important. And then Scattered through this scene, mostly in the southern parts of Pangaea, were the dinosaurs. Tiny, bipedal, lightly built, often a meter or so long, often a few kilograms in weight. Animals like the very earliest Eoraptor-grade dinosaurs in the rocks of what is now Argentina. They ran fast, ate small things, and kept out of the way of the rauisuchids. If you had been a Triassic naturalist with a clipboard and a notebook in the early Carnian, you would have ranked them as a curiosity. You would not have predicted that they were about to inherit the world. There were a few mammals already, but only a few, and they were small. The cynodonts, the lineage that would eventually produce true mammals, included animals like Synognathus, the size of a medium dog, with a more upright stance, and probably some kind of fur. They had survived the end Permian crisis 15 million years before, and they had carved out a small place for themselves in the Carnian ecosystem. They were not yet warm-blooded in the modern sense, probably, but they were on the way. Most of them were nocturnal, judging from their eye sockets. They came out at night, when the rauisuchids were quieter, and they hunted insects and small reptiles in the moonlight. The point of this part is simple. The world we are about to watch the rain destroy was a real world. It had its own rules, its own animals, its own ecosystems. It had been running in something close to its Carnian configuration for tens of millions of years. It was, in its way, perfect at being what it was, and it was about to be erased. Somewhere, off the western shore of Pangaea, in what we would now Part 3, the crack in the Pacific. To understand the storm that ended the old Triassic world, you have to leave the continent behind and go out to sea. Specifically, you have to go to a region of the late Triassic Pacific Ocean that does not, today, exist as ocean floor. Every piece of seafloor that was there at the time has since been subducted, recycled, or accreted onto the edge of a continent. The volcanic province that did the damage now sits, in pieces, embedded in the side of North America. Geologists call it the Wrangellia Large Igneous Province. The name comes from the Wrangell Mountains of southeastern Alaska, where the basalts are most spectacularly exposed today. They run, in fragments, all the way down through the Yukon and into Vancouver Island in British Columbia. If you have ever driven the Alaska Highway, or hiked in Wrangell State, Elias National Park, you have walked on the rocks that ended an era. A large igneous province, or lip, is exactly what the name says. It is an event in which an unusually massive amount of magma is erupted in a relatively short geological window, almost always associated with mantle plume activity. They are rare. There are perhaps 20 of them spread across the last 600 million years of Earth history. Almost every one of them coincides, in the rock record, with a major biological crisis. The end Permian extinction came with the Siberian traps. The end Triassic extinction came with the Central Atlantic magmatic province. The end Cretaceous, although mostly an asteroid, also coincided with the Deccan traps. The Wrangellia eruption sits in the middle of that list. It put roughly 1 million cubic kilometers of basalt into the late Triassic atmosphere and ocean over a window of about 2 million years, between roughly 234 and 232 million years ago. To get a feel for that volume, imagine taking the entire country of France, every square kilometre of it, and burying it under 1 solid kilometre of black volcanic rock. That is the magnitude. And it did not erupt all at once. It erupted in pulses, with quiet years in between, and each pulse left its own chemical signature in the global record. Most of the eruption was submarine. The seafloor cracked and bled, hot lava meeting cold water, generating enormous plumes of steam and pillow lavas thick enough to bury entire ocean trenches. There were subaerial pulses too, where the basalt piled high enough to break the surface, and pyroclastic ash columns rose into the stratosphere. From a distance, if there had been a distance from which to observe it, the late Triassic Pacific would have been a darkening sea, gas escaping from the surface in bands, ash in the air, mercury vapour rising on the wind. The chemistry of an LIP is what does the damage. When magma like that erupts, it brings with it carbon dioxide, sulfur dioxide, mercury vapor, hydrogen chloride, and ash. The sulfur dioxide forms aerosols that briefly cool the planet, a kind of volcanic winter. The carbon dioxide warms it on a longer timescale, sometimes for hundreds of thousands of years. The mercury condenses globally and falls as a thin film of poison into sediments everywhere on the planet. Each of these chemicals leaves its own fingerprint in the rock record. It is the mercury fingerprint that closed the case on Rangelia. In 2018, a research group led by Jacopo Dal Corso, working at the University of Padua, published a paper in Geology that documented mercury anomalies in Carnian rocks all across Europe. The anomalies lined up, in time, with the Rangelia eruption. They lined up, in space, with what we would expect from an LIP-driven mercury fallout pattern. They were the smoking gun. Until then, we had suspected Rangelia. After then, we knew. The carbon isotope record told us about the climate response. When light carbon, the isotope 1 squared C, floods the atmosphere and ocean from a volcanic source, the ratio of 1 squared C to 1 tube C in marine carbonates drops. We call this a negative carbon isotope excursion, or CIE. The CPE rocks contain not one CIE, but four. Four discrete, sharp drops in carbon ratio, spaced a few 100,000 years apart, each followed by a slow recovery. This pattern tells us the eruption pulsed. The climate did not go straight from dry to wet. It pulsed wetter, dried slightly, pulsed wetter again, dried, and so on, 4 times, over about 1 million years. The absolute dating came from uranium-lead zircon ages, drawn from ash beds preserved in sedimentary sections. The Pignola Abriola section in the Lago Negro basin of southern Italy is the modern reference. It contains thin layers of volcanic ash, and the zircon crystals in those ashes are excellent natural clocks. Researchers have dated the top of the Carnian stage to 227.27 million years ago, with a precision of about 110,000 years. Working backward, the CPE phase falls neatly into a window beginning around 234 million years ago and ending around 232 million years ago. The trigger debate is not quite settled. Rangelia is the consensus driver, but its volume alone may not be sufficient to explain the magnitude of warming we see in the rocks. Some researchers, most notably Mika Rule and his collaborators, have argued that warming destabilized seafloor methane hydrates and that the methane release amplified the carbon isotope signal beyond what Rangelia could produce alone. Others argue that orbital forcing, the slow wobble of Earth's tilt and orbit, paced the 4 pulses on top of a Rangelia-warmed baseline. The truth is probably some combination of all 3: volcanic carbon, methane amplification, and orbital pacing. There is a useful comparison here. The Siberian traps, which erupted at the end of the Permian about 252 million years ago, put roughly 4 million cubic kilometers of basalt into the world. They are widely thought to have caused the worst mass extinction in the history of life. The Central Atlantic Magmatic Province, which erupted at the end of the Triassic about 201 million years ago, put roughly 2 million cubic kilometers into the world. It caused the end Triassic mass extinction. Rangelia, at 1 million cubic kilometers, is smaller than both. But the climate effect of an LIP depends on more than its volume. It depends on how fast the magma erupted, on the carbon content of the magma, on the configuration of the continents at the time, and on whether the eruption melted carbon-bearing crustal rocks on its way up. Rangelia hit a sweet spot. It was small enough not to sterilize the planet, large enough to break it. If you stood on the Carnian Pacific shore in the wrong year, you would have known something was wrong. Sulfur on the wind, ash on the tide line. The sea, normally a healthy blue-green from algae and carbonate platforms, beginning to look strange. Mercury falling, invisibly, on every surface for thousands of kilometers in every direction, the atmosphere thickening, the light dimming, and, far away, far inside Pangaea, the mega-monsoon already alive was about to feel the heat. Part 4. The switch. The physics of the switch is, on paper, simple. A warmer atmosphere holds more water vapor. The relationship is described by an equation called the Clausius-Clapeyron relation, which goes back to 19th century thermodynamics. In rough numbers, every degree Celsius of warming allows the air to hold about 7% more water. Multiply that by a planet, by a few degrees of warming sustained over hundreds of thousands of years, and you have a hydrological cycle that is moving substantially more water around than it used to. More evaporation from the oceans, more clouds, more rain. Now layer that warming onto a supercontinent that was already running a mega-monsoon system. The pre-CPE mega-monsoon delivered seasonal rain to a band of Pangaea every year. After Rangelia warmed the atmosphere, that band of seasonal rain became a band of nearly continuous rain. The seasonal extremes weakened, the wet season expanded. Rain that used to fall in 3 months began to fall in 9, then 12, and the geographic footprint widened. Areas that used to be on the dry margin of the monsoon belt fell inside it. Areas that used to be inside the monsoon belt became saturated. The continent began to switch. Slowly at first, in the geological sense. From the standpoint of an animal alive at the time, the change might have been slow enough that no individual generation noticed. From the standpoint of geology, it happened in an eye blink. Across 1 to 2 million years, the lithology of the planet flipped. You can see this flip in the rocks. The signal is strong enough that it does not require sophisticated instrumentation to detect. You can find it with a hand lens and good eyes. In the Italian Dolomites, the type section is the Heilig-Kreuz Formation. The rocks below it are pale, carbonate-dominated, the remains of shallow tropical platforms in the western Tethys. The rocks above are silicoclastic, that is, they are made of sand and silt and clay washed down from continental rivers rather than precipitated from seawater on a reef. The transition is sharp. Pale grey carbonate gives way to dark grey shale, and the dark grey shale contains the fingerprint of intense chemical weathering, on land the kaolinite clay that forms when rocks are subjected to long, heavy rainfall. In the northern calcareous Alps of Austria, the type section is the Rheingraben shale. Here too you find the same signal, carbonate platforms below, dark siliciclastic shales above. The Rheingraben has been studied for over 100 years, and recent high-resolution mineralogical work, published by Lucanida and Lucanida in 2021, has documented the kaolinite spike with unprecedented clarity. The signal also turns up in South China. The Yangbachong section, in the eastern Tethys, records the same lithological flip and contains the same 4 carbon isotope excursions. Yidong-sun and his colleagues, in 2019, even documented black shale layers, a sedimentary rock that forms when organic-laden mud accumulates under low-oxygen water. Black shales are usually a sign that the ocean has lost much of its capacity to circulate oxygen to its lower layers, often because warming has weakened bottom water mixing. The switch is also visible in the Newark supergroup of eastern North America, where lake deposits record alternating wet and dry phases that shift toward the wet during the CPE window. It turns up in the Doswell Formation of Virginia. It turns up in southern Italy at the Aglianico section, where all 4 CIEs are preserved in tight stratigraphic order. It turns up wherever Carnian rocks are well preserved. Pollen and spore records, what palynologists call the palynological signal track, the same change at finer resolution. Pre-CPE assemblages are dominated by Dicroidium flora seed ferns. During the wet pulse, those assemblages are progressively replaced by spore-pollen mixtures, characteristic of wetter, more closed canopy vegetation, with conifer and lycophyte pollen rising and fern spore content shifting. What does all this mean in practical terms, for the planet. It means that for 1 million years, the global hydrological cycle was running at a higher level than it had been before, and large parts of Pangaea that had previously been desert or near desert were now living in something more like a tropical wet climate. Rivers that did not exist before began to cut new channels. Floodplains expanded across what had been salt flats. Lakes formed in basins that had been holding only seasonal puddles. Soils developed where soils had not been able to develop leached, acidic, kaolinite-laden soils, the chemical fingerprint of wet weathering. The wet pulse buried, in the process, an enormous quantity of organic matter. Plants growing on the new wet floodplains died and fell into anoxic standing water. The water, oxygen poor, did not allow normal decomposition. Instead, the plant matter accumulated, layer on layer, eventually compacting into peat, and eventually, over geological time, into coal. Many of the major coal seams in Central Europe, North China, the Southern Caucasus, and the Middle East trace their origin to this wet pulse. The fossil fuel reserves we are mining today, in large part, are the buried biomass of the Carnian Pluvial episode. The modern industrial economy is, in a perfectly literal sense, burning the storm. There is a particular kind of weathering signal that goes with this kind of climate. Geologists call it kaolinization. Kaolinite is the white, soft, ultra-fine clay you might know from porcelain. It forms when feldspar minerals in granite and other rocks are subjected to long, intense rainfall. The rain leaches out the soluble cations, and what is left is the chemical residue of total weathering. Kaolinite-laden soils are what you find under modern Indonesian rainforests, under modern Amazonian floodplains, under modern Congolese tropical wetlands. To find them in the rocks of Central Europe and northern Italy and Austria is to find a tropical fingerprint in a continental record. The CPE is the moment in geological time when the chemistry of the world's soils across most of Pangaea looked Indonesian. That alone tells you the magnitude of the change. The interior of a supercontinent does not produce kaolinite-laden soils unless something extreme has happened to its weather. Something extreme had. Stand in the modern Dolomites. Look at one of those famous pale walls of mountain carbonate, where the thrust-faulted limestones have been exposed by glacial erosion. Run your eye up the cliff. At a particular height, the colour shifts. The pale carbonate gives way, in a band perhaps a few tens of meters thick, to darker, finer-grained rock. Then, eventually, the carbonate returns. That darker band is the Carnian Pluvial episode, written into the side of the mountain. You can find this event with a pair of eyes and a clear day. It is one thing to read the rocks. It is another to ask what happened to the animals while the rocks were being laid down. The rain, after all, did not just rearrange the geology, it killed. Part 5. The drowning of the old world. Extinction events do not look like extinction events from inside them. They do not arrive as a single catastrophic afternoon. They arrive as a pressure that an ecosystem cannot quite keep up with. A reef that does not recover after a bleaching season, then bleaches again the next year and the next. A herd of dicynodonts that finds the watering hole has moved, and that the new watering hole is 200 kilometers further, and that the journey does not finish. A conodont species that was producing fewer eggs every spawning season for 10,000 years, and at some point simply did not spawn at all. Extinction is not a moment. It is the aftermath of pressure that exceeded capacity. For the marine animals of the Carnian, the pressure was extreme. Conodonts, small, eel-like animals with mineralized tooth elements that we use as one of the most precise paleo-time markers, we have went through the worst of it. Recent quantitative work by Tomimatsu and his colleagues, published in 2021, documented the loss of approximately 1/3 of all conodont species during the CPE. For an entire animal phylum to lose a third of its species in 1 million years is a major event. We do not have a clear modern parallel except possibly current insect declines, and those are still in their first century. Ammonoids, the coiled, intelligent, predatory cephalopods that ran the open seas of the Mesozoic, had a hard time too. Many lineages disappeared. Others went through a rapid turnover, with new lineages radiating into vacated ecological space. Ammonoid evolution is fast under pressure. They are well known to paleontologists as one of the great laboratories of evolution, and the CPE is one of their classic test events. Bivalves, gastropods, brachiopods, and crinoids all suffered regional collapses, especially in the shallow tropical tethys, where the warming and acidification were most pronounced. Brachiopods, those bivalve-shaped animals that are not actually bivalves, but a separate phylum that has been quietly losing ground since the Permian, never really recovered to their pre-Carnian numbers. The CPE was one of the moments in their long decline. The most visible casualties were the reefs. Stony coral reefs, that is, reefs built by scleractinian corals, the lineage that still builds reefs today, had only existed for a few million years at the time of the CPE. They were a fairly recent ecological invention, built by a coral group that had descended from earlier non-reef building forms in the Middle Triassic. They had set up shop on shallow tropical platforms across the Tethys. The dolomite carbonates we have been talking about are, in part, the remains of those reefs. The CPE killed them. The combination of warming, increased terrestrial runoff, smothering coral surfaces in mud, and ocean acidification dissolved skeletal carbonates faster than juvenile corals could grow them. The reefs collapsed across the world. There is a multi-million-year reef gap in the late Triassic. Recovery does not begin in earnest until the Nourian. The lineage of corals that survived the CPE and that recolonized reef habitats afterwards is the lineage that today builds the Great Barrier Reef and every other tropical reef on the planet. On land, the casualties were different. The dicynodonts, those barrel-bodied tusked synapsids, went through a sharp decline. They had been the dominant terrestrial herbivores for tens of millions of years. After the CPE, their numbers and their species count drop substantially, although a few large lineages persist into the Nourian. The dicroidium flora, on which much of the dicynodont herbivore community depended, collapses across southern Pangaea around the same time. Whether the floral collapse caused the dicynodont collapse or vice versa is part of an ongoing debate. They almost certainly amplified each other. The pseudosuchian archosaurs lost ground, although unevenly. The big rauisuchids declined particularly hard. Atosaurs persisted, but with reduced numbers and a narrower range of forms. Phytosaurs continued to dominate river systems for the rest of the Triassic, but they are a long-snouted river specialist, and their continued existence is partly because the new, wetter world expanded their preferred habitat. Their lineage will be killed off, eventually, at the end Triassic mass extinction. The big debate, which I want to put to you honestly, is whether the CPE rises to the level of a true mass extinction. The Big Five list, as it has been taught for 40 years, was canonized by David Raup and Jack Sepkoski in 1982. It is built on a particular statistical signal in the marine fossil record. By that signal, the CPE is large but does not quite cross the threshold for the canonical list. But the science has moved. In 2021, Lu Jin and his colleagues argued in Earth Science Reviews that when you account for the full ecological and biotic disruption terrestrial as well as marine, including the cascading effects of Wrangellia, the methane amplification, the 4 pulsed CIEs, and the reset of entire vertebrate communities, the CPE is comparable in significance to the events on the canonical list. They are not quite arguing for a big six, but they are arguing that the CPE has been historically underweighted because the framework that ranked extinctions was put together before we understood it. You can decide by the end of the night where you want to file it. What I will tell you is this: The casualty list is real. The reefs collapsed, the conodonts crashed, the dicynodonts dwindled, the seed ferns retreated, the rauisuchids declined. A whole biotic regime was being dismantled by a million years of unrelenting wet weather and the chemistry that came with it. There is one more casualty I should mention, because it gets overlooked. The radiolarians, microscopic, single-celled marine organisms with elaborate silica skeletons, also went through a major turnover in the CPE. Radiolarians are some of our most precise paleo-time markers in offshore marine settings. Their skeletons preserve well, they speciate quickly, and they are abundant. The CPE radiolarian record shows extinction and rapid replacement, with new species rising from refugia in the post-CPE early Norian. They are a tiny detail at the scale of a planetary crisis, but they tell us that the disruption reached every level of the ocean, from the seafloor reefs to the surface plankton, from the ammonoid swimmers in the middle of the water column to the silica-shelled drifters at the limits of light. But extinction is half the story. Once the old world is dismantled, something has to step into the empty rooms, and in the rocks above the wet pulse, something does. It walks on two legs. It has hollow bones. It has air sacs threading through its skeleton. It has eyes that face forward, jaws that open wide, and no clear understanding of how lucky it has just been. The dinosaurs are about to inherit the world, and we know, now, exactly when they begin. Part 6. The Forgotten Footprints. If you want to know when an animal actually lives somewhere, you do not look for its bones, you look for its tracks. Bones tell you where an animal died and was buried in a way that allowed preservation. That is a narrow and biased filter. An animal that died in the wrong setting, a mountain forest, a fast-flowing river, a high desert, almost never makes it into the fossil record. An animal that died in the right setting, a quiet floodplain, a shallow lake, a low-energy delta, has a much better chance. The fossil bone record is not a sample of the population. It is a sample of the population that died in the right places. Tracks are different. A footprint is left wherever an animal walked across soft sediment that subsequently dried, hardened, and was buried. If your dinosaur has been walking around for a few million years across a continental interior, you will find its tracks across a continental interior. The track site record is a much wider net than the bone record. It is also harder to read. You cannot easily tell from a footprint alone exactly what species made it. But for a question like, where did dinosaurs live, and how many of them were there before they died and got into the bone record, tracks are extraordinary. In 2018, Massimo Bernardi, a paleontologist at the Muse Museum of Sciences in Trento, Italy, together with Piero Gianola, Fabio Petti, Paolo Mietto, and the British paleontologist Mike Benton, published a paper in the Journal of the Geological Society. The title was modest, the implications were not. The paper was called Dinosaur Diversification Linked with the Carnian Pluvial Episode. What Bernardi and his colleagues did was look carefully at trackways in the Italian Dolomites. The Dolomites have an unusually complete record of Carnian-aged rocks, and over a century of Italian fieldwork has produced a well-documented set of track sites in different formations at different stratigraphic levels. By comparing the trackways in formations below the CPE wet pulse to the trackways in formations above it, Bernardi could ask a question that body fossils could not answer. Below the wet pulse, the trackways are dominated by pseudosuchians, crocodile-line forms, heavy-footed quadrupeds, the kinds of animals you would expect from an early Carnian fauna. There are dinosaur tracks too, but they are a small minority. Maybe 5% of the recognizable trackways, maybe less. Above the wet pulse, the picture changes. Dinosaur trackways become much more common. By the late Carnian, in the Dolomite track site record, dinosaur footprints are the dominant trace. The transition is not gradual across the entire stratigraphic range. It is concentrated, sharp, in the rocks immediately overlying the CPE interval. This was the first hard evidence, the first quantitative, large area evidence that the dinosaur radiation was not just a coincidence with the CPE, but a response to it. The body fossil record, which had been our main tool, had hinted at the same story. The track site record clinched it. Within a geological eye blink of the wet pulse ending, dinosaurs had moved across northern Pangaea in numbers that pseudo-Suchians no longer matched. Bernardi's argument is straightforward. The CPE caused a major extinction. That extinction emptied out ecological space. Dinosaurs, which had existed in small numbers as a marginal group in southern Pangaea, expanded into that space. They moved fast. They radiated within a few 100,000 to a few million years. By the time the late Carnian rocks of the Dolomites were being deposited, dinosaur trackways were the dominant trace. This is, by the way, why fieldwork still matters in paleontology. The Bernardi paper did not require a new fossil. It required someone to walk the Dolomites carefully, to know which trackways were where, to read the stratigraphy with a fluent eye, and to ask a quantitative question of an existing dataset. The science of dinosaur radiation was rewritten by, essentially, a careful walk. If you go to Muse in Trento today, you can see casts of these trackways. The museum has been excellent about presenting them in the geological context that gives them meaning. You stand in front of a cast of a Carnian trackway, three-toed and bipedal, the imprint of an early theropod-like dinosaur, and the museum tells you what it is, when it was made, and what was happening in the world at the time. It is one of the few paleontological exhibits I know of that takes a single trace fossil and uses it as a key to a global reorganization. There is something philosophically interesting in this story. The bones tell you who died. The tracks tell you who lived. To understand the post-CPE world, we needed to spend less time in the morgue and more time on the floor. We needed to know where the dinosaurs walked, not where they fell. And it was their footprints that finally opened the door. I want you to picture, for a minute, the scene that produced one of those tracks. A late Carnian floodplain in what is now northern Italy. The wet pulse is mostly past, but the world is still wetter than it used to be. Pools in old riverbeds, mud on the high water lines, heavy clouds, water dripping from broad-leaved cycads. A small bipedal predator, a metre or so long, three-toed feet leaving sharp impressions in the soft brown mud as it crosses an open patch of ground. Behind it, a cluster of similar prints made by another animal travelling the same way. Behind them, the entire geological record of an ecological reorganization that we, 232 million years later, would only finally piece together by walking the same ground in the right order. There is one more thing the trackways can tell us, and it is something the bones almost never can. They can tell us about behavior. A trackway preserves a sequence of footprints made by a single animal moving across a single substrate over a short span of time. From the spacing of the prints, you can estimate stride length. From stride length and a few measurements of foot anatomy, you can estimate hip height. From hip height and gait pattern, you can estimate speed. Some Carnian dinosaur trackways preserve evidence of an animal accelerating, decelerating, or changing direction. Some preserve groups of animals walking together, suggesting either family groups or herding. The trackway record of the early dinosaur world is, in a way, a movie of a moment that has otherwise come down to us only as a heap of disarticulated bones. It tells us that very soon after the storm ended, there were small bipedal predators running across wet floodplains in groups, and that there were others crossing the same ground alone. They were already, at this earliest moment, behaviourally varied. The trackways tell us something happened. The bones tell us what was making them. To meet those bones, we have to leave Italy and travel to the southern hemisphere to a particular dry valley in Argentina that has produced more questions about dinosaur origins than any other site on Earth. And it is in those rocks that the real names start. Part 7, Ishigualasto and the First Dinosaurs. The Valle de la Luna sits in San Juan province in northwestern Argentina. Today, it is desert. The wind carves the rocks into improbable shapes. The light, in the late afternoon, makes the sandstones glow orange. It is one of the most strange and beautiful places I know of, and it is the most important place on Earth for the question of dinosaur origins. The rocks exposed in the Valle de la Luna are the Ishigualasto Formation. They are sediments laid down on a late Triassic floodplain with rivers, lakes, and seasonal wetlands. They have been dated by uranium-lead zircon ages from interbedded volcanic ash layers to approximately 231.4 million years ago, plus or minus 300,000 years. That puts them right after the close of the Carnian Pluvial episode in the early years of the post-storm world. In those rocks, paleontologists have found, over more than half a century of careful fieldwork, a snapshot of an ecosystem in transition. Most of the vertebrates in the Ishigualasto fauna are still old-school late Triassic forms: rhynchosaurs, dicynodonts, pseudosuchians. Dinosaurs are still a minority of the assemblage by abundance, but they are present, and they are extraordinary. The most famous of them is Eoraptor lunensis. The name means dawn thief from the Moon Valley. It was named in 1993 by Paul Sereno, Catherine Forster, Raymond Rogers, and Alfredo Moneta. Eoraptor is small. It would have stood about a meter long, weighed maybe 10 kilograms, and walked on two legs with a small head, slender arms, sharp small teeth, and a long balancing tail. Its anatomical position in the dinosaur family tree has shifted across decades of analysis. It has been called a basal theropod. It has been called a basal sauropodomorph. It has been called a basal saurischian, sitting near the splitting point of the two great dinosaur lineages. Whatever it formerly is, it sits very near the trunk of the family tree. It is one of the closest things we have to a first dinosaur that we can hold in a museum drawer. If Eoraptor is small, Herrerasaurus ishigulastensis is large. It was named earlier, in 1963, by Osvaldo Reig. It reaches 3 to 4 meters in body length. It has a long, narrow skull with serrated teeth designed for slicing meat. It walks on its hind legs and has reduced, grasping forelimbs. It is, functionally, a mid-sized predator, not the apex of the Ishigualasto food chain, but a serious carnivore in its own right. The apex of the food chain is still occupied by Saurasuchus galilei, the rauisuchid we met earlier, which is bigger and heavier than any of the dinosaurs in the same rocks. Then there is Eodromaeus murphy, named in 2011 by Ricardo Martinez and his colleagues. It is small, light, fast, possibly closer to the ancestor of theropods than Eoraptor is. And there is Saturnalia tupiniquim, found further north in the Santa Maria Formation of southern Brazil, which is roughly the same age as the Ishigualasto. Saturnalia is an early sauropodomorph, on the lineage that will eventually produce the long-necked giants of the Jurassic and Cretaceous. These four animals, Eoraptor, Herrerasaurus, Eodromaeus, Saturnalia, are what the early dinosaur world looks like. Small to medium-sized, almost all bipedal, almost all fast, omnivorous to predatory. None of them are huge. None of them are armoured. None of them have the elaborate ornamental anatomy that later dinosaurs will develop. What they share, anatomically, is a particular hip configuration. They have a perforate acetabulum, a hole in the hip socket, where most other reptiles have a closed socket. They have a fully erect, parasagittal limb posture, with the legs underneath the body rather than splayed to the sides. They have hollow bones with internal struts. They have, probably, a system of air sacs threading through their bodies, related to the bird-style respiratory system, though this would have to be inferred rather than directly observed in the bone record. Why did these features matter in the post-CPE world? The honest answer is that we are not sure. Erect posture is more energetically efficient than splayed posture. Hollow bones are lighter and allow larger body sizes for less skeletal mass. Air sacs improve oxygen extraction. Each of these is a small advantage. Together, they may add up to a meaningful one, but none of them on their own is a knockout. The ecological context is what matters most. The CPE crisis emptied ecological space. Dicynodonts declined. Rauisuchids declined. The dicroidium flora, which Dicynodonts had grazed, retreated. The new wet world had new vegetation, new river systems, new floodplains, new prey, and new competition. Dinosaurs, with their efficient locomotion and rapid maturation, may simply have been better positioned to expand. Mike Benton has argued this for years, that dinosaur dominance was less a story of competitive replacement and more a story of opportunism in the wake of climate-driven extinction. When you walk the Valle de la Luna today, the absence of green plants and the strangeness of the eroded forms make it feel like you are on Mars. But 231 million years ago, you would have been standing on a wet floodplain. There would have been water in the rivers. There would have been ferns at the river edges. There would have been small bipedal predators darting between the cycads. There would have been the first sauropodomorphs browsing in groups. There would have been the heavy footsteps of a Saurosuchus somewhere in the trees, reminding everyone that the old world had not entirely let go. It is worth pausing on what makes the Isigualasto record so unusual. Most late Triassic terrestrial fossil sites preserve isolated bones, often weathered, often jumbled. The Isigualasto preserves articulated skeletons in something close to life position. The reason is taphonomic. The depositional setting was a wet floodplain with seasonal flooding, and animals that died near the river margins were quickly buried in fine sediment before scavengers could disarticulate them. The preservation is exceptional. We have Eoraptor skulls with their teeth still in their sockets. We have Herosaurus hind limbs still attached to their hips. We have Saturnalia skeletons that can be reconstructed almost in full. This is not the norm in Triassic paleontology. Most Triassic dinosaurs are known from fragments. To have something like Isigualasto for the very earliest part of the radiation is a piece of geological luck the discipline has been quietly grateful for since the 1960s. The dinosaurs were small then, they were minor. They were a family of light-footed bipeds, mostly under 4 meters long, mostly under 200 kilograms, mostly outclassed by the larger pseudosuchians around them. In the year 231 million BCE, no observer would have called them the future, but the future they were, and the rivals they replaced are worth their own part of the story. Part 8. The Rivals That Lost. I want to spend some time with the animals the dinosaurs replaced. They are some of the most remarkable creatures the planet has ever produced, and they are mostly forgotten. They deserve better. The pseudosuchian archosaurs are the lineage on the crocodile side of the Great Archosaur split. Modern crocodiles and alligators are their last surviving descendants. But in the Triassic, pseudosuchians were not just crocodiles, they were everything. They had filled almost every available niche on the supercontinent. They were the apex predators. They were the armored herbivores. They were the riverine ambush hunters. They were the pursuit predators. They were, depending on the niche, bipedal or quadrupedal, herbivorous or carnivorous, agile or armored. They had radiated to fill the world, and they had been doing it for 30 million years before the CPE arrived. Let me give you a tour of the lineages. The Rauisuchids were the top predators. Saurosuchus galilei from the Isigualasto Formation was 6 to 7 meters long, with a tall, robust skull and a bite force that we estimate could have crushed a small modern crocodile's skull. Postosuchus in North America was similar, heavy-bodied, tall-skulled, terrestrial, walking either bipedally or on all fours, depending on its mood and the species. Prestosuchus in Brazil reached comparable sizes. These were animals that fed on Dicynodonts, the size of cattle, and on whatever else they could catch. They were, in the early Carnian, the closest analogues to a Tyrannosaurus rex that the planet would have until the actual late Cretaceous, and they were almost everywhere. The Atosaurs were the armored herbivores. Atosauroid scaglii and its relatives walked on 4 legs with their backs paved in heavy, bony armor, shoulder to tail. They had small heads with low-crowned teeth and slightly upturned snouts that may have been used for rooting in soil like a pig. Their armor, lying in the rocks, is some of the most distinctive vertebrate fossil material of the whole Triassic. You can recognize an Atosaur scute on first sight. The phytosaurs were the river specialists. They had long, narrow snouts and sharp, conical teeth, and they hunted fish and amphibians at the water's edge. Their nostrils sat high on their skulls, just in front of their eyes, a beautiful adaptation for breathing while submerged. They look so much like crocodiles that they were originally classified as crocodile relatives. They are not. They are an older, more basal, pseudo-Suchian lineage. Their crocodileness is convergent a body plan that works for that ecology and gets evolved more than once. The Poposauroids were a smaller and stranger group. Some of them, like Ephigia, were lightly built bipeds with small heads and slim limbs. Some of them, like Lotosaurus, had sails on their backs. They are the lineage that demonstrates how flexible the pseudo-Suchian body plan actually was, how willing it was to experiment. After the CPE, all of this collapses to varying degrees. The Rauisuchids are particularly hard hit. By the early Norian, large Rauisuchids are scarce. By the late Norian, they are functionally gone. Atosaurs persist longer, but with reduced species counts. Phytosaurs do well, expanding into the new, wetter world, persisting through the Norian and into the Ratian, only to be killed off at the end Triassic mass extinction. Poposauroids fade. What killed them? The honest answer is we are not sure, and there are 2 camps. One camp argues for direct competition. Dinosaurs, with their efficient, erect posture, hollow bones, air sacs, and probable elevated metabolism, were simply better at being terrestrial vertebrates than the pseudo-Suchians were. Once dinosaurs got going, they outcompeted pseudo-Suchians in head-to-head ecological encounters and progressively pushed them out of niche after niche. This is the classical competitive replacement model. The other camp, and Mike Benton is one of its leading voices, argues for opportunism. Dinosaurs did not push pseudo-Suchians out. The CPE pushed pseudo-Suchians out by killing off the prey they ate, the vegetation they depended on, and the climatic conditions they were tuned for. Dinosaurs, in this view, walked into vacated ecological space rather than fighting for it. The Bernardi track site work, with its sharp transition rather than gradual replacement, supports this version more than competitive replacement. The truth, as usual, is probably some of both. The CPE created the opening. Dinosaurs, with their suite of locomotor and metabolic advantages, were the lineage best positioned to expand into the opening. There was probably some direct competition in particular niches, but the larger story is one of an ecological vacuum being filled by the lineage best able to fill it. The crocodilomorphs, the lineage that, eventually, produces modern crocodiles, survive this crisis by going small and going semi-aquatic. The earliest true crocodilomorphs, like Saltopasuchus, are slim, bipedal, terrestrial, small-bodied animals, not much bigger than a domestic cat. From there, their lineage shifts toward water, eventually producing the large aquatic predators we have today. Modern crocodiles are the surviving fragment of what was once an entire continental fauna. There is one counterfactual I want to put on the table. Imagine that Rangelia had erupted half as much basalt. Imagine that the CPE had been milder. Imagine that the warming had peaked at half its actual value, that the 4-pulsed CIEs had been smaller, that the wet pulse had lasted 300,000 years instead of 1 to 2 million. The Rauisuchids might have survived. The Atosaurs might have held their ranges. The Dicynodonts might have stayed dominant, and the dinosaurs might have stayed marginal. Without the CPE, there might be no dinosaurs as we know them. No long-necked sauropods, no armoured ankylosaurs, no horned ceratopsians, no theropod lineage that, at the very end of the Cretaceous, produces a small group of feathered survivors that we call birds. The world we know is partly a consequence of how much basalt erupted in the eastern Pacific 234 million years ago. It is also worth noting that some pseudoseuchians, against the odds, came back. The crocodilomorph lineage that survived the CPE eventually rebounded. By the late Jurassic, marine crocodilomorphs called metriorhynchids were patrolling shallow seas with paddle limbs and hypercircle tails, looking like swimming nightmares. By the early Cretaceous, terrestrial notosuchians in South America had evolved into hoofed, herbivorous, fast-running forms, true ground crocodiles, competing with small dinosaurs. By the modern day, only a handful of crocodilomorph species remain, all semi-aquatic, all roughly conservative in body plan. But the lineage that nearly disappeared in the CPE has had its share of evolutionary experiments since, and most of them are gone now. The crocodile under the dock today is the last leaf of a family tree the storm pruned almost to the trunk. The CPE, in other words, is not just a story about the storm and what it killed. It is a story about contingency. We are here, and the world looks the way it does, because of one chain of geological events that could easily have gone otherwise. Tonight, somewhere, a chickadee is calling in a winter forest, and that calling is possible because Pangaea erupted just enough. The animals had changed, the plants had changed too, and the new forests are worth their own part. Part 9. The New Forest. I want you to picture, for a moment, what a Carnian forest looked like before the storm. You walk into it, in the wetter band of southern Pangaea, and the trees overhead are not pines, they are not oaks. They are something else. Their fronds fork at the tip-to leaflets, sharing a single branch in a pattern that no plant alive today produces. This is the Dicroidium flora. Dicroidium was a group of seed ferns. Their leaves were elaborately divided, sometimes a meter long. Their reproductive structures sat in male and female cones, distinct from the leaves. They were not flowering plants. They were not conifers. They were a separate experiment in seed-bearing vegetation that ran for tens of millions of years across the southern hemisphere of Pangaea, from what is now South America to South Africa to Australia to Antarctica. They were the keystone vegetation of southern Pangaea. They fed the Dicynodonts. They sheltered the rhynchosaurs. They built the floors of the floodplains. They were everywhere. And they collapsed during the CPE. The collapse is not a single event. It is a slow attrition through the wet pulse and into the early Nourian. By the time the rocks above the CPE interval are being deposited, Dicroidium is in steep decline across most of its former range. By the time the Nourian is well underway, it is gone from most places where it had been dominant. The floras of the southern hemisphere are reorganizing. What replaces them? Mostly conifers. Conifers had existed for a long time before the CPE. They first appear in the late Carboniferous, more than 300 million years ago. Through the Permian and the early Triassic, they were a minor but persistent component of the floras. The CPE is the moment when they take over. Specifically, 3 modern conifer families take off in the post-CPE world. The Pinaceae, the pine family, are still around, in modern coniferous forests of the northern hemisphere. The Araucariaceae, including modern monkey puzzle trees, and the Araucaria of the southern hemisphere, are direct descendants of the post-CPE radiation. The Cherulepidaceae are extinct now, but were enormously important across the rest of the Mesozoic. These conifers are different from Dicroidium in some specific ways that matter. Their leaves are needle-like or scale-like, much smaller surface area, lower water loss, more heat-tolerant. Their wood is denser. Their seed cones are larger and more elaborate. They are taller, often. They grow into closed canopy forests rather than open gallery woodlands. Bennettitals, those cycad-like plants with elaborate insect-pollinated cones, also diversify in the post-CPE world. They are extinct today, having been replaced by flowering plants in the Cretaceous. but in the Mesozoic, they were one of the dominant plant groups. Their reproductive structures hint at the early development of complex insect-plant pollination relationships, the kind of co-evolutionary dance that flowering plants would later perfect. The implications for the animals are substantial. Dicynodonts had teeth and jaws tuned for shearing the divided fronds of Dicroidium. Conifer foliage is tougher. It is more fibrous. It is less nutritious per bite. It demands a different jaw, a different gut, a different feeding strategy. Dicynodonts struggled with this transition. The early sauropodomorph dinosaurs, with their longer necks, more efficient gut fermentation, and ability to browse high canopy vegetation, were better suited to the new forests. The vegetation shift may have been as important to the dinosaur radiation as the extinction was. The dinosaurs did not just get a better world, they got a better world with better food. Wildfires changed too. Dicroidium fern-dominated floras burned with a particular regime frequent, low-intensity ground fires that fed on the soft fronds and renewed the vegetation. Conifer-dominated forests burn differently. They produce more resin, hold more dry biomass higher off the ground, and burn hotter and less often, but with much greater intensity when they do. The charcoal record across the CPE interval shows this transition clearly. Soils transformed as well. Pre-CPE soils in dry settings were calcium-laden, often calcrete cemented, with shallow profiles and low organic content. The wet pulse leached them, washed away the soluble cations, concentrated kaolinite at the top, and dropped the pH. Post-CPE soils are deeper, more acidic, more weathered, more leached, more like modern tropical soils. Where the conifer forests took root, the new soils held them. This vegetation reorganization is why I want you to understand the CPE as more than a climate event. It is a structural reset of the entire terrestrial biosphere. The CPE flips the chemistry of the atmosphere, the chemistry of the oceans, the chemistry of the soils, the structure of the forests, and the trophic structure of the vertebrate fauna. The change is not a single change. It is a cascade. There is a particular conifer family I want to single out because it has a story almost no other plant can match. The Cherulepidaceae were the dominant conifers across most of Pangaea through the Triassic, Jurassic, and most of the Cretaceous. They had small, scale-like leaves and unusual reproductive structures that produced a distinctive pollen type called Classopolis. We can trace their history with that pollen alone. Classopolis dominates Mesozoic palynological assemblages from poles to equator. They radiated in the post-CPE world, ruled the Mesozoic forests, and went extinct at the end of the Cretaceous, taken out by the same asteroid that ended the dinosaurs. They are gone now, but for 170 million years, they were the most common tree on the planet. The CPE made them. The KPG extinction unmade them. They are a small reminder that even the longest tenures are bracketed by the great geological resets. When you walk through a pine forest today, through a stand of Pinus or Picea, with the needles soft underfoot, the canopy closed overhead, the forest floor shaded and quiet, you are walking through a Carnian inheritance. The first time the world looked something close to this, in the southern hemisphere at least, was in the millennia after the Carnian Pluvial episode. The conifers that survived and radiated then are the ancestors of the conifers we are walking under now. The Araucaria trees that grow today in the Andes, in southern Brazil, in New Zealand, in Australia, those direct, slow-growing, monkey puzzle-leaved trees with their distinctive, symmetrical branching, are descendants of the post-CPE radiation. When you stand under an Araucaria, you are standing under a tree whose lineage outlived the storm, outlived the dinosaur extinction, outlived the rise of mammals, and is still here, now, doing what it was already doing 230 million years ago. There are very few living things you can say that about. The forests had changed. The animals had changed. And in the oceans, something even more fundamental was being invented. The storm was not just rearranging the world above the water. It was rebuilding the world under it, one microscopic skeleton at a time. Part 10. A storm that built the modern ocean. The most important thing the CPE did, in the long run, may not have been killing the dicynodonts, or radiating the dinosaurs, or rebuilding the forests. The most important thing it did may have been building the modern ocean. I want to introduce you to the calcareous nanoplankton. These are microscopic, single-celled algae a few microns across, smaller than a grain of pollen, that build their cell walls out of tiny plates of calcium carbonate called coccoliths. They live in the surface waters of the open ocean. They photosynthesize. They reproduce, sometimes explosively, in immense blooms. And when they die, their tiny calcite skeletons sink slowly toward the seafloor, taking carbon out of the surface ocean and depositing it on the bottom. This process is called the biological pump. It is one of the master regulators of Earth's atmosphere. By moving carbon from the surface ocean, which exchanges with the atmosphere, to the abyssal ocean and seafloor, which does not, calcareous plankton remove carbon dioxide from the atmosphere over geological time, modern Earth has, in its surface ocean, an enormous machine made of trillions of microscopic algae that quietly regulates the planet's climate. Calcareous nanoplankton appear in the rock record during or just after the Carnian Pluvial episode. Before the CPE, the open ocean's surface waters had different plankton diatoms had not yet evolved. The modern dinoflagellate radiation was incomplete, and there was no organized mechanism for moving calcium carbonate from the surface to the seafloor in the way we have today. After the CPE, this changes. The biological pump, as we know it, begins to operate. Why this matters? The modern atmosphere depends on this pump. Earth's climate stability, its ability to recover from carbon perturbations like volcanic eruptions, like methane releases, like asteroid impacts, depends on the biological pump's capacity to move carbon out of the atmosphere on timescales that matter. Before the CPE, that capacity was low. After the CPE, it was high. We live in a calcareous, nanoplankton stabilized world. We did not before this storm. Coral reefs follow a similar arc. The first stony coral reefs, built by scleractinian corals, the lineage that builds reefs today, appeared in the Middle Triassic. They were a recent invention. The CPE collapsed them. There is a multi-million-year gap in the reef record across the late Triassic. Reef recovery does not begin in earnest until the Norian. The corals that survived and rebuilt the reefs were a small subset of the original scleractinian range. That subset is the lineage that has built every coral reef since. Every reef in the modern ocean, the Great Barrier Reef, the reefs of the Coral Triangle, the Caribbean fringing reefs, descends from CPE survivors. If you have ever snorkeled over a tropical reef, you have been swimming over the descendants of one of the great survival stories from the long past. The lineage that built the reef under your fins survived 1 million years of warm, acidified, runoff-clogged Tethyan water. That capacity for survival is part of what reefs have always carried with them. The marine reptile communities reorganized too. Ichthyosaurs, the dolphin-shaped marine reptiles, had appeared in the early Triassic, but they were modest in size. After the CPE, ichthyosaur lineages diversify and produce some of the largest predatory marine animals the planet has ever produced. The shastasaurid ichthyosaurs of the Norian and Ratian reached 20 meters in body length, larger than any modern whale shark. Their evolution into gigantism was made possible, plausibly, by the ecological vacancies the CPE opened in the marine vertebrate community. Plesiosaurs are the other story. The first true plesiosaurs, long-necked, paddle-finned marine reptiles, appear in the post-CPE late Triassic. They will dominate the seas of the Mesozoic for the next 165 million years until the KPG extinction at 66 million years ago. Modern marine biology has nothing exactly like a plesiosaur. But the Loch Ness monster archetype that lives in the popular imagination is, basically, a plesiosaur. Their lineage was a CPE invention. Lissamphibians, the modern frog, salamander, and caecilian crown group trace their origin to roughly this window. Modern frogs, in particular, are a CPE story. The earliest unambiguous frog stem fossils appear in the early Jurassic, but the molecular clock estimates push the Lissamphibian crown group back into the late Triassic, in the post-CPE period. Every frog you have ever heard calling at night is the descendant of a lineage that began in the aftermath of this storm. Turtles diversify across the late Triassic too. The earliest unambiguous turtle, Progonochles, dates to the Norian and is fully turtle-like, with a formed shell. The lineage's deeper origin is debated. Some paleontologists trace turtle ancestry into the Permian, others closer to the Triassic, but the turtle radiation as we recognize it is a post-CPE phenomenon. Lepidosaurs, the lineage that produces lizards and snakes today, gain ground in the late Triassic and onward. Their crown radiation is later, but the post-CPE world is when they begin their march to dominance. When you put all of this together, what you have is a CPE that does not just kill an old world, it builds a new one. The new world has all of the structural features we still rely on. Calcareous nanoplankton in the surface ocean, modern stony coral reefs, long-necked marine reptiles, modern amphibian crown groups, modern turtle ancestors, modern lepidosaur ancestors, modern conifer forests, dinosaurs. This is why the CPE matters more than its modest place in the textbook would suggest. The big five mass extinctions get their names because they killed the most. The CPE deserves a name because it built the most. Almost everything in your life that is alive, from the parrot in a window, to the pine tree on a ridge, to the coral in a reef, to the chicken on your plate, is part of a lineage that begins or radiates dramatically after this storm. There is one more piece of biology I want to flag before we move on. The dinoflagellate single-celled algae with whip-like flagella that move them through the water also expanded substantially in the post-CPE oceans. Some modern dinoflagellate lineages cause the toxic blooms we now call red tides. They are part of the marine plankton that sit alongside calcareous nanoplankton and diatoms in the modern carbon cycle. Their post-CPE diversification is part of the same wave of evolutionary innovation that built the modern surface ocean. Almost everything alive in the open sea today has, somewhere in its lineage, a CPE chapter. Now, 2 hours is a long time to spend on a single event. I have been telling you the central story, but the storm reaches further than that, into other corners of paleontology and paleoclimate that have been turning up in recent research. We have time, before we close, for a few of those corners. They will take us from the Atacama Desert to the Arctic permafrost, to the riverbeds of the American Southwest, to the climate models running in modern laboratories. Each one is a different way of asking the same question. What did the storm leave behind, and how can we tell? Part 1. The 2024, pterosaur from the Atacama. Northern Chile, in the modern day, contains some of the driest country on Earth. The Atacama Desert holds the record for the longest documented period without rainfall in any place where rainfall is sometimes measured. There are weather stations in the Atacama that have not received a measurable drop in over 50 years. It is, at human scale, one of the closest analogues to pre-CPE Pangaea our planet currently offers. What is interesting is that, despite the dryness, paleontologists in Chile have been quietly working through late Triassic and early Jurassic strata that nobody used to map carefully. The rocks are there. The fossils are there. The fieldwork has been thin until recently because the country's paleontological tradition focused, for decades, on later periods. That has been changing, and the recent results have been remarkable. In particular, work over the last several field seasons has produced new pterosaur material from the Atacama region. This is significant for a specific reason. The Triassic pterosaur record is thin. Pterosaurs first appear in the late Triassic, somewhere between roughly 220 and 210 million years ago, and most of the early body fossils come from a small number of European sites. New South American material extends the geography of the early pterosaur radiation and tells us how widely the lineage had spread by the end of the Triassic. Let me explain what a pterosaur is, because the public confusion is consistent. Pterosaurs are not dinosaurs. They are flying reptiles on the archosaur lineage, but not on the dinosaur branch. Their wings are not made of feathers. Their wings are leathery membranes stretched between an elongated fourth finger and the side of the body. Their bones are hollow, like dinosaur bones, but their hollowness is even more pronounced. Pterosaur bones are tubes with very thin walls and internal struts. Their bodies range, across the lineage's full 150 million year history, from sparrow-sized to the size of a small aircraft. The late Cretaceous Ajdarchids, the largest known flying animals ever, had wingspans of 10 to 12 meters. The late Triassic pterosaurs were modest by comparison. They were small, lightly built animals, more like leathery seabirds than the giants of the Cretaceous. Animals like Eudimorphodon from Italy had wingspans of about a meter, narrow heads with sharp, multicusped teeth, and probably ate insects and small fish. Other Triassic forms include Pitanosaurus, Caelesteventus, and Priondactylus, each with its own slightly different body plan, all sharing the basic pterosaur architecture: hollow bones, elongated fourth finger, leathery wing membranes stretched between finger and body. They were, by every measure I can think of, an experiment that worked. The question that recent Chilean material helps answer is, how widely had the pterosaur lineage spread by the end of the Triassic? The answer, increasingly, is very widely. Pterosaurs were not just a European phenomenon. They were a Pangaean phenomenon. Their lineage radiated across the supercontinent in the post-CPE window, alongside the dinosaur radiation, alongside the conifer radiation, alongside everything else. This connects back to the CPE story in a specific way. Pterosaurs needed three things to evolve. They needed a body plan that could support powered flight. They needed an evolutionary ancestor that could plausibly produce that body plan. And they needed an ecological vacancy in the air. Before the CPE, the air was largely empty of large flying animals. Insects were there, of course, but no vertebrate had yet conquered powered flight. The late Triassic, in the post-CPE world, is when that vacancy gets filled. What did the post-CPE world offer to early pterosaurs that pre-CPE Pangaea did not? Plausibly, the answer is biomass. The wetter, more vegetated post-CPE world produced more insect biomass. More vegetation means more leaf litter, more standing water, more seasonal pools, more places for insect larvae to develop. More insects means more food for small flying vertebrates. The earliest pterosaurs were almost certainly insect feeders. There is also a possibility that the wetter world produced the climatic conditions for thermal soaring, the technique modern albatrosses use to fly enormous distances at low metabolic cost. The combination of warm, wet tropical belts and persistent regional temperature gradients could have produced reliable thermal columns that an early pterosaur could exploit. This is speculation. The pterosaur fossil record is sparse enough that direct ecological evidence is hard to come by. But the broader picture, the CPE, opens up new ecological space, and the pterosaur lineage radiates into a part of that space is consistent. The point of this part is not really about pterosaurs. It is about the geography of recovery. The CPE story has often been told as a European or Tethyan story because the type sections and the most studied rocks are in Europe. But the recovery was global. South America has its dinosaur evidence in the Ishigualasto and Santa Maria formations. South America has its flying reptile evidence, increasingly, in Chile and Argentina. South America has its plant evidence in the post-CPE conifer floras. The new world that the storm built was a world that radiated everywhere there was space. When you stand in the modern Atacama, looking at the dry plain stretching to the horizon under a sky that almost never opens, you are standing in a geography that is, in some respects, more like pre-CPE Pangaea than anywhere else on Earth. The dryness is similar. The bare ground is similar. What is different, of course, is the atmospheric chemistry, the ocean configuration, and the fact that 230 million years of evolution stand between you and the ancestors of the animals that walked here. There is a particular Chilean field season worth noting. Researchers from the Universidad de Chile and several international collaborators have been working sites on the western side of the Andes that contain late Triassic and early Jurassic vertebrate material in unusual abundance. The work has been slow and quiet. There are no big press releases. There is a steady accumulation of papers in journals like the Journal of South American Earth Sciences and Cretaceous Research and the Journal of Vertebrate Paleontology. Every paper adds another piece. A jaw fragment with diagnostic teeth, a wing finger phalanx, a partial skeleton in a road cut. The southern Pangaean record of early flight is slowly coming into focus. It will probably take another decade of fieldwork before the picture is full. Paleontology rewards patience. The rocks have been waiting 220 million years. They can wait another 10. The pterosaurs are gone. Their lineage was killed off at the end of the Cretaceous. But the ground they walked on in southern Pangaea, in what is now Chile, is still being read by patient paleontologists. And the rocks are still telling the story of how the post-CPE air filled with leathery wings. The CPE opened the air. It also, more soberingly, opened the question of what releases of carbon do to a planet over a million-year window. And that question, in the modern world, has a specific name. It is methane. And modern researchers are racing to understand what the CPE can teach us about it. Part 12. The methane mystery in modern permafrost. Modern climate science has a problem. The problem is methane. Carbon dioxide is the main concern in modern atmospheric chemistry because it is the most abundant greenhouse gas being released by industrial activity. Methane gets less attention, partly because there is less of it in the atmosphere, partly because it has a shorter residence time. But methane is molecule for molecule, a much more potent greenhouse gas than carbon dioxide. And there are enormous reservoirs of frozen methane on Earth, locked into permafrost soils and seafloor hydrates that climate scientists worry about destabilizing. This is where the CPE comes in. The CPE may, in part, have been a methane event. The argument goes like this. Pangaea released a lot of carbon dioxide. The carbon dioxide warmed the atmosphere. The warming reached the seafloor, particularly in shallow continental margin settings, where seafloor temperatures are most sensitive to surface conditions. Seafloor methane hydrates, frozen in the sediments, began to destabilize. Methane bubbled up. Methane has a strongly negative carbon isotope signature. It is much lighter in WK2C than ordinary atmospheric carbon. So when it floods the atmosphere, it produces a deeper negative carbon isotope excursion than carbon dioxide alone could produce. The 4 CIEs we see in the CPE rocks may, in part, be amplified by methane. Mecherule and others have argued this for years. The case has strengthened with newer, high-resolution isotope work. There is still disagreement on how much methane was involved versus how much was just direct volcanic carbon dioxide. But the methane hypothesis is now a serious contender in the explanation of CPE warming. Why does this matter for the modern day? Modern Earth has, in its high-latitude soils and shallow seafloor sediments, an enormous reservoir of frozen methane. Permafrost soils in Siberia, Alaska, and the Canadian Arctic store between 200 and 1,000 gigatons of carbon. Much of it in forms that release methane upon thawing. Submarine methane hydrates, in shallow Arctic continental shelves and in some lower latitude settings, store similar quantities. As the Arctic warms, and the Arctic is warming at 3 to 4 times the global average rate, these reservoirs are starting to release. Methane plumes have been documented bubbling up from the seafloor of the East Siberian Arctic shelf. Permafrost ponds across Siberia and Alaska are emitting methane at measurable rates. The flux is not yet catastrophic, but the trajectory is concerning, and the question on every climate scientist's mind is whether modern warming could trigger a runaway methane release of the kind that may have amplified the CPE. The CPE, in this framing, is a natural experiment. It tells us what happens when an external warming source, Pangaea, in this case, perturbs a methane-storing climate system. The resulting amplification can be substantial. The CPE rate of warming was roughly 0.5 degree to 1 degree Celsius per 10,000 years, give or take. Modern anthropogenic warming is closer to 1 degree Celsius per century. We are warming the planet, in other words, between 5 and 10 times faster than the CPE warmed it. That speed differential is not a comfort, it is a warning. The CPE happened slowly enough for many species to migrate, adapt, or evolve. Even at that pace, the CPE caused a major extinction event. Modern warming, faster, may not give species the time the CPE did. And if methane amplification kicks in, if the modern Arctic begins to release methane at rates comparable to what may have happened during the CPE, the warming will accelerate even further. Recent paleoclimate work in 2023 and 2024 has used refined isotope records from the CPE to put tighter bounds on the methane release rates. The numbers are not encouraging. The methane release that is being inferred for the CPE, if the methane interpretation is correct, is comparable in magnitude to the upper bound estimates of what could happen in the modern Arctic if warming continues, unchecked. It is the closest geological precedent we have for a methane-amplified anthropogenic warming scenario. I want to say this carefully. Paleoclimate is not deterministic. The CPE is an analogy, not a prediction. Modern Earth is not Pangaea. The continental configuration is different. The ocean circulation is different. The starting CO2 is different. The modern biosphere has different responses than the Carnian biosphere, but the chemistry of carbon and the physics of warming are the same. And when paleoclimatologists look at the CPE record, they see a planetary system that, when perturbed, amplified the perturbation through methane and produced a major biotic crisis. There is also, I should say, a positive side to this work. Studying the CPE tells us how the Earth system recovered. After the wet pulse, after the methane release, after the 4 CIEs, the climate dried out. Silicate weathering the slow chemical process by which mountain rocks absorb carbon dioxide eventually drew down the excess carbon. The atmosphere returned to something more like its pre-CPE state, although never exactly, and the biosphere stabilized in its new configuration. The recovery took, optimistically, a few million years. Pessimistically, more. If we want to know what the modern world looks like a few million years after a large carbon perturbation, the CPE gives us one of our better records. The biosphere that emerges is different from the one that went in. The animals are different. The plants are different. The ocean chemistry is different. But there is a biosphere. The planet does not become Venus. It becomes a new version of itself, with most of the old removed and a new set of inheritors in place. There is one further wrinkle I want to add, because it makes the methane connection more concrete. The carbon released during the CPE was, by the best current estimates, between 5,000 and 20,000 gigatons. Modern human emissions, since the start of the industrial era, total about 700 gigatons of carbon. We are, in other words, well below the CPE's total release, at least so far. But the CPE released its carbon over 1 to 2 million years. We are releasing ours over a few centuries. The instantaneous flux is what matters for ocean chemistry, atmospheric chemistry, and biological response. By that measure, modern emissions are running at rates roughly 100 times faster than even the CPE's pulses. The CPE is not a worst-case scenario. It is, in the rate domain, a moderate scenario. The actual current trajectory of anthropogenic emissions is something the CPE record cannot, on its own, tell us much about. It is something we are, in real time, finding out. It is a strange comfort. The Earth has done this before. It will, presumably, do it again. The question is, what we, as a species, want our role in that to be. Survivors, inheritors, and casualties. The CPE rocks do not answer this for us. They simply tell us that the question is real. In the meantime, while modern researchers run their isotope ratios in laboratories from Padua to Wuhan, fieldwork continues on the bones of the CPE world's losers. And in the American Southwest, recent excavations have been turning up some remarkable things. Part trees, a mass grave of phytosaurs. In the high desert of northeastern Arizona, just east of the Petrified Forest National Park boundary, there is a unit of red and grey rock called the Chinle Formation. The Chinle is late Triassic. It is younger than the CPE. Most of the exposed Chinle is Norian and Retian, post-dating the wet pulse by 10 to 15 million years. But it preserves the world that emerged from the post-CPE recovery, and it has been one of the most important late Triassic terrestrial fossil sites in North America for over a century. The Chinle is famous for its petrified wood. The fossilized tree trunks scattered across the modern Badlands are mostly conifers, mostly Araucarioxylon, early relatives of modern monkey puzzle trees. They were buried in the ash and mud of a late Triassic floodplain and silicified atom by atom into stone. The petrified forest is a remnant of the post-CPE forest reorganization we have been discussing. You can walk among the logs of trees that grew in the world the storm built. The Chinle is also famous for its phytosaurs. I want to remind you who phytosaurs were. Phytosaurs were long-snouted, semi-aquatic, late Triassic archosaurs on the pseudo-Suchian side of the family tree. They look extraordinarily like crocodiles. They are not crocodiles. They are an older lineage that evolved a similar body plan, independently convergent evolution in action. Their nostrils sat high on their skulls, just in front of their eyes, allowing them to breathe while almost entirely submerged. Their skulls were narrow and full of conical teeth. They hunted fish, amphibians, and probably any small terrestrial animal that came too close to the water's edge. Phytosaurs ran the rivers of late Triassic Pangaea. They were everywhere. The Chinle Formation alone contains phytosaur material from at least half a dozen genera and species, ranging from 1 meter or 2 long up to 6 or 7 meters in length. They were, ecologically, the river apex predators of the post-CPE recovery period, and they died, sometimes, in mass grave-like accumulations. Recent fieldwork in the Chinle, including programs run out of the Petrified Forest National Park Research Station, the Berkeley Museum of Paleontology, Virginia Tech, and the Field Museum of Chicago, has documented phytosaur bone beds with hundreds of individuals. These are not normal accumulations. Normal Triassic vertebrate fossils come in 1s and 2s, sometimes in articulated skeletons, more often in scattered bone fragments. A bone bed with hundreds of individuals of a single taxon means something specific happened. The leading interpretation is drought. The post-CPE world was, on average, wetter than the pre-CPE world, but it was not uniformly wet. There were dry phases, there were seasonal droughts, there were multi-year droughts. As water levels in rivers and lakes dropped, phytosaurs concentrated at shrinking water bodies. They competed for shrinking territories. They starved as fish populations crashed. They died in numbers in the same place at the same time. The next wet pulse buried their bones together. Geological time compressed the event into a single layer of rock, and modern fieldwork has been unearthing those layers one bone bed at a time. There is something extraordinary about this. The phytosaurs survived the CPE. Their lineage thrived in the wetter post-CPE world. They expanded across the supercontinent. And then, at the regional scale, they died in droves at the boundaries of the new wet world, where the water turned out to be unreliable. The phytosaur lineage, despite its CPE survival, did not make it out of the Triassic. The end Triassic mass extinction, around 201 million years ago, killed them off. Their relatives, the crocodilomorphs that had gone small and semi-aquatic during the CPE, did make it through. From them, the modern crocodile lineage descends. The phytosaurs, for all their convergence with crocodiles, left no descendants. What does this tell us about the world the CPE built? It tells us that the new world was not a simple one. It was not just wetter. It was variable. It had wet pulses and dry pulses. It had river systems that expanded and contracted. It had ecological winners that, in turn, met new pressures and lost. Phytosaurs are a reminder that surviving one extinction event does not guarantee surviving the next. They lived through the CPE. They radiated. They thrived. And then they died at the next bottleneck. The bone beds of the Chinle are, in a sense, the cemeteries of the post-CPE world. They are the places where the inheritors of the storm met the next pressure and could not adapt fast enough. They are reminders that geological time is full of partial successes, lineages that survive one crisis only to be culled in the next. There is also, in the Chinle, a record of the earliest North American dinosaurs. Animals like Coelophysis, bowery small, slender theropods, perhaps 2 to 3 meters long, appear in late Chinle rocks of New Mexico. The famous Ghost Ranch quarry in northern New Mexico produced hundreds of articulated Coelophysis skeletons from a single bone bed, all preserved in fine mudstone, all clustered together as if they had died in a single event. Drought, again, is the leading interpretation. The post-CPE recovery world was a world of feast or famine river systems, and dinosaurs, as well as phytosaurs, paid the price when the famine years came. The Ghost Ranch fossils are, in their way, a North American mirror to the Ishigualasto fauna further south, and they extend our picture of the dinosaur radiation across the supercontinent. Standing in the petrified forest today, with the silicified Araucaria trunks scattered across the Badlands and the Chinle Formation eroded into mesas and canyons, you can trace the whole post-CPE story in the rocks under your feet. The conifer wood tells you the forest reorganization worked. The phytosaur bone beds tell you that surviving a wet world was not the same as surviving everything. It is, I think, a useful reminder. In our own moment, we are watching a climate perturbation play out in real time. We are seeing winners and losers in the global biota. We are seeing some species expand and others contract. We are seeing surprising outcomes, the loss of charismatic species, the radiation of generalist invaders, the local collapse of ecosystems that seemed stable. What the phytosaurs of the Chinle remind us is that the post-perturbation world is also a perturbation. There is no point at which the storm ends and stability resumes. There are only the pressures of the next moment, and the next, indefinitely. Every species alive is an interim survivor. This is heavy material for a sleep documentary, I know, but I think the long-time perspective on it is, in its way, calming. The Earth has been through this before. It will go through it again. The biota survives, in different configurations, indefinitely. The question is not whether life persists. The question is which lineages persist and which cannot keep up. And one of the tools we now use to ask that question is climate modelling. The atmospheric circulation patterns of pre-CPE Pangaea, of the wet pulse, of the post-CPE recovery, they are all being reconstructed in modern computer models. And what those models are telling us is, in some ways, the most surprising part of the whole story. Part 14. The Mega Monsoon Reborn. If you want to predict the climate of the future, you have to understand the climate of the past. This sounds obvious. It has not always been obvious. For most of the 20th century, climate science was largely a contemporary discipline, focused on observation of the modern atmosphere and ocean. Paleoclimate, the climate of the long past, was a separate field, often housed in geology departments, sometimes barely talking to atmospheric science. That is changing. In the last 30 years, climate scientists have increasingly turned to the geological past as a laboratory for testing their models. Modern computer models, global climate models, or GCMs, can be initialized with paleogeographic configurations and run forward to see what climate they produce. If the model produces a climate that matches the rocks, the model has been validated. If it does not, the model has a problem. The CPE is one of the events climate modelers have been particularly interested in. Why? Because the Pangaean megamonsoon, the seasonal continental scale circulation that defined the Triassic, is a circulation pattern that has no exact modern parallel. There is no supercontinent today. The closest analogue to Pangaea is the Asian landmass, which produces the modern South Asian monsoon. But Asia is much smaller than Pangaea, and the South Asian monsoon is much less extreme than the Pangaean megamonsoon must have been. When climate scientists model the Pangaean megamonsoon, they get rainfall patterns that are, in some respects, more extreme than anything observed in the modern world. The summer wet season delivers enormous quantities of rain to particular bands of the supercontinent. The winter dry season is brutally arid. The contrast between wet and dry is much sharper than any modern monsoon. What happens to that mega-monsoon when you add Rangelia-style warming? The models say it intensifies dramatically. The wet season expands, rainfall rates rise. Geographic extent broadens. The dry season weakens. In some model runs, the mega-monsoon transitions from a seasonal phenomenon to a near-continuous one in the wettest tropical bands. The wet pulse, in other words, may have been not just a wetter version of the mega-monsoon, but a fundamentally different circulation regime, a mega-monsoon that no longer turned off in winter. This is what the rocks suggest too. The lithology of the wet pulse is consistent with a regime where rainfall is sustained for years at a time, not just monsoonal seasons. The kaolinite-laden shales, the coal beds, the leached soils, these all imply persistent wet conditions, not extreme seasonality. The implications for modern climate science are significant. We are increasing atmospheric carbon dioxide. We have a smaller continental configuration, but Asia is large, and the South Asian monsoon system is one of the most populous area-affecting climate systems on the planet. As warming continues, the South Asian monsoon may transition into a more extreme state, wetter, wet seasons, more intense rainfall events, perhaps, eventually, a less seasonal regime. The CPE provides upper bounds on what is possible. It tells us, from rock evidence, what a supercharged monsoon looks like over geological time. It tells us how the biosphere responds to that supercharged monsoon. It tells us that the response is dramatic, that ecosystems reorganize, that whole groups of animals lose their footing while others gain it. For the long-term future, there is another consideration. Plate tectonics will not stop. In about 250 million years, the continents will reassemble into a new supercontinent that geologists have informally named Pangaea Ultima. When that happens, a new mega-monsoon will form, and the Earth will, for the first time since the Triassic, host a continental-scale monsoonal regime. The CPE is, in that sense, a preview of a recurring climate state, one that the planet has had before and will probably have again several times before life on Earth comes to whatever close it eventually does. Recent 2024 work using newer and higher resolution GCMs has been refining these projections. The models are not entirely consistent. Different teams use different boundary conditions and produce slightly different mega-monsoon strengths and geographic extents. But the broad pattern is robust. A warm, supercontinental Earth runs a much more extreme hydrological cycle than the one we live in now. There is something philosophically interesting about this. We tend to think of the modern climate as the default, as the way Earth's atmosphere is supposed to work. The CPE rocks tell us otherwise. The modern climate is one mode of operation among several. A supercontinent-scale megamonsoon is another. A snowball Earth is another. A hot anoxic ocean is another. Earth has run through all of these before, sometimes more than once, and will run through them again. The atmosphere we inherit is not the only atmosphere the planet can produce. It is just the one we happen to live in. There is one specific modelling result worth highlighting. In recent simulations of the post-CPE atmosphere, researchers have shown that the wet pulse may have produced what climate scientists call hyperactive cyclogenesis, a regime in which tropical and mid-latitude storm systems form more frequently, last longer, and reach more intense peak strengths than they do in the modern atmosphere. The fingerprint of this in the rock record would be deeper river channels, larger floodplain deposits, more frequent debris flow units in the sedimentary record. We do find these features in CPE rocks. The match between model and record is one of the strongest pieces of evidence we have that the wet pulse was driven by atmospheric dynamics, not just by surface evaporation. The planet's air, in other words, did not simply contain more water. It moved that water more violently, more often, and more widely than it does now. When climate modelers run their simulations, they are, in a sense, asking the planet to remember. They are giving the model the geographical and chemical conditions of a past world and asking it to reproduce that world's climate. The planet, through the model, says, yes, given those conditions, this is what I do. Then the modelers change the conditions toward the modern, and the planet says, yes, given those conditions, this is what I do. Then they change them again toward the future, and the planet says, yes, given those conditions, this is what I will do. The conversation with the planet, conducted through equations and rock data and computer simulations, is one of the most remarkable scientific developments of the last few decades. It is also one of the more humbling. The planet has answered questions we had not thought to ask. The CPE is one of those answers. So is, I suspect, the future we are running toward. We have followed the storm from the seafloor crack to the dinosaur radiation to the modern climate model. There is one part left. It is the part where I ask what, after all of this, the storm has actually given us, and whether we have noticed. Part 15. What the storm left us. It is 234 million years after the rain began. Look around. The room you are in, the window in front of you, if you have one, the trees outside, the bird, if there is one, calling somewhere, the landmass under your house, the continent you live on, the atmosphere your lungs are processing. All of it is connected by an unbroken chain of inheritance to a million-year storm that drowned a supercontinent and rebuilt the world from the wet ground up. Let me tally what the Carnian Pluvial episode produced. It produced the dinosaurs as we know them. Before the storm, dinosaurs were a small, marginal lineage of bipedal southern Pangaean predators, less than 5% of the vertebrate fossils in their rocks. After the storm, they expanded into vacated ecological space, radiated across the supercontinent, evolved into the great body plans of the Mesozoic, and ruled the land for 165 million years until an asteroid 66 million years ago ended their tenure. The dinosaurs are not entirely gone. One of their lineages survived. The theropod branch, specifically the Maniraptoran subgroup, produced the birds. Every chickadee, every parrot, every chicken on every farm, Every pigeon in every city, every gull on every coast, every peregrine falcon over every cliff is a living dinosaur and a living legacy of the Carnian Pluvial episode. The next time a sparrow lands on your windowsill, the lineage on its windowsill is 234 million years older than humans. It produced the modern conifer forests. The Pinaceae, the pine family, and the Araucariaceae and the Cherolepidaceae diversified in the post-CPE window. The forest you can walk through in any pine forest is descended from that radiation. The lumber in the walls of the room you are in, if it is softwood, traces its lineage to the post-storm world. It produced the modern coral reefs. Every reef in the modern ocean, the Great Barrier Reef, the reefs of the Coral Triangle, the Caribbean fringing reefs, the Red Sea reefs, is built by scleractinian corals descended from the lineage that survived the CPE. The bleaching crisis the modern reefs are facing from anthropogenic warming is the most recent in a series of pressures their lineage has weathered for more than 230 million years. They are in trouble. They have been in trouble before. It produced the modern carbon cycle. Calcareous nanoplankton, the microscopic algae that drive the biological pump, appeared in surface oceans during or shortly after the CPE. The stable atmosphere of our planet is, in part, a Carnian invention. It produced modern amphibians, modern turtles, modern lepidosaur ancestors, the first true plesiosaurs, the giant ichthyosaurs. The structural fauna of the next 230 million years was, in large part, assembled in the post-storm window. It produced fossil fuels, substantial coal reserves across Central Europe, North China, the Southern Caucasus, and the Middle East are buried plant matter from the wet pulse. The industrial economy of the last 2 centuries is, in the most literal sense, burning the Carnian Pluvial episode and putting its carbon back into the atmosphere, undoing, accidentally, one of the storm's chemical legacies. What did the CPE take? It took the Rauisuchids, the apex predators of the early Carnian. It took most of the dicynodont species. It took the dicroidium flora that had defined southern Pangaea for tens of millions of years. It took the first stony coral reefs. It took roughly 1/3 of conodont species and major fractions of ammonoid and brachiopod families. It took ecosystems that had been stable for so long that they had probably seemed permanent to anything that could have observed them. There is a serious philosophical point here, and I want to put it to you plainly. The world we live in is a survivor world. It is not a designed world. It is not an inevitable world. It is the world that emerged when a particular volcanic province in the late Triassic Pacific erupted at a particular rate, when methane hydrates may have amplified the warming, when 4 pulsed carbon isotope excursions reorganized atmospheric and ocean chemistry, when the rain fell for 1 million years and rewrote the continents. The biosphere that emerged is the biosphere that fit through that bottleneck. Every species alive today is an inheritor. Every species missing today from that pre-Carnian world is a casualty. The biosphere did not choose this. It survived this. If Rangelia had erupted twice as much basalt, perhaps no biosphere would have made it through, no birds would call from the trees today, and no humans would eventually arrive to ask what the storm meant. Or, in the other direction, if Rangelia had been smaller and the rain had only fallen for a few 100,000 years, the Rauisuchids might have held on, the dicynodonts might have stayed dominant, the dinosaurs might have stayed marginal, and the world we live in would be unrecognizable. You and I are not the result of inevitability. We are the result of a 1,000,000-year storm whose exact magnitude was, in the largest sense, contingent. This is a calming thought, I find, despite how unsettling it sounds at first. Contingency means the future is not predetermined either. The biosphere is not running on rails. It is moving through the next contingency now, and how it moves through is partly up to those of us alive to make decisions about it. Modern anthropogenic warming is not the CPE. We are not Rangelia. The atmospheric carbon we are releasing is being released much faster than the CPE released it. But the total magnitude is, if we continue on current trajectories, in the same general range. The biosphere will respond. There will be winners, there will be losers. The lineages that get through will be the ancestors of whatever future biosphere emerges. Some of them will be species nobody has ever imagined yet, evolved in the pressure of a stress event. We do not know what species. The CPE rocks give us patterns, not names. They tell us warming reorganizes forests, that ocean chemistry amplifies surface stress, that vacated niches fill with new lineages from unexpected groups, and that 1,000,000 years feels long to a vertebrate but is short to a planet. The CPE killed the Rauisuchids and built the modern biosphere. The end Permian killed almost everything and then rebuilt almost everything. The end Cretaceous killed the dinosaurs and gave us the world the mammals inherited. If Earth's history were a 24-hour clock, the Carnian Pluvial episode happens at roughly 13 minutes past 11 at night and lasts about 30 seconds. Humans show up at 1 minute, 17 seconds before midnight. The rain that built our world was, in the planet's experience, a very brief shower. We are walking through what it left behind, and most of us have never noticed. Tonight, somewhere on this planet, the next reset may already be beginning. The seas are warming, the Arctic is releasing methane, the reefs are bleaching, the forests are burning. The atmosphere is taking on a chemistry it has not held since the Carnian, perhaps not since well before. The geology is patient. It is always patient. It will, in its own time, sort the inheritors from the casualties and the next biosphere from the present one. We get to vote, in our small way, on which lineages we take with us into the next chapter. Sleep well. The storm has come before. It has ended before. Whatever comes next is, for now, a question the rocks have not answered. They will. They always do. The rain is over. The world is new.